This lecture is about correlation, and this lecture is a good transition between where we have just been in the book with looking at statistical significance and chi-squared and difference of means, and translating that over into learning regression, where we're going after this, and we'll have about a month in class to talk about that. I said in class before that regression is just fancier correlation. That's an oversimplification, but it is very true in the sense that when we think about the statistical models that we're going to be learning, the formulas are really just trying to calculate the statistical significance that a correlation exists. So if we can understand at a most basic level what a correlation is, then we can begin to more easily understand in the coming weeks what regression is. So this is a very fundamental concept, very simple concept, but very fundamental concept to understanding where we're going. When I say a correlation, I mean a relationship between two or more things. So if we say that two things are correlated, that means that they are related, they co-occur, they co-vary is another very common verb, they share a common pattern, they seem to be related in some way. Though if you remember back to when we discussed spuriousness, correlation does not mean causation. And here you should be thinking about the example of per capita cheese consumption and deaths from being entangled in bed sheets. Those two phenomena somehow, weirdly, correlate very strongly, but they don't cause each other in a way that is logically clear. So all correlation is trying to determine whether patterns in two or more things overlap. It is not causation. We can quantify correlation, which is where we're going in this lecture. We saw a little bit of that in the last lecture. We looked at chi-squared. The chi-squared test is a test of whether two variables measured at the nominal or the ordinal level are related. It doesn't tell us anything about the strength necessarily of that relationship, but it starts to get you into the habit of thinking about whether relationships exist in a quantifiable way that we can then use our rules of statistical significance to talk about the odds that that relationship is real or not. One of the correlation methods that I'll teach you in this PowerPoint enables you to look at whether two or more phenomena or variables are correlated. Chi-squared can only look at two variables, but we can actually calculate correlation on 3, 4, 5, up to infinity. And the Pearson's R that we'll learn in this lecture is where we'll do that. So correlation, again, is just whether two things are related and how much. A model is a set of conceptual relationships that explains variation in a dependent variable. This is where most of you are with your papers. You're trying to develop models to explain your phenomenon of interest. You're thinking about theoretically what are the other variables that you should be looking at as independent variables to explain the variation in a dependent variable. Turnout might be a function of gender, race, income, education, and something attitudinal like alienation from government, for example. And if those are the things that we think give us predictive power over understanding whether people voted or not, then that's our model for understanding turnout. Regression is the new term here. Regression just refers to a family of statistical methods that look at or measure the correlation between the mean value of one variable and corresponding values of another variable. So regression, and there are multiple different regression techniques that we have, there is no one singular type. They all build on the basic correlation that we're going to look at in this lecture and try to quantify that further so that we can then, in a mathematical way, talk about how much two things actually relate. As I showed you in class on the board, but I didn't put it in the PowerPoint, it's not necessarily necessary knowledge for you. There are many different types of regression, and so it is important to understand how some of those things differ. There are different types of regression models that you use for different types of dependent variables. I will be teaching you two types of regression in this class. One of them is ordinary least squares regression that is used for interval or ratio level data. Technically, there is a different kind of regression for ordinal data, like an agree-disagree scale. But as I said in class, oftentimes we do things that are a little mathematically incorrect when the bias that results from them is not strong. I'll talk about that a bit more later. We can use ordinary least squares, or OLS, on some ordinal level data. So it's an adaptable tool. The other kind of regression I'll be teaching you is logistic regression. That's where we'll end the class. And that is regression that looks at dichotomous dependent variables. 0-1 phenomenon. Did you vote or not? Did you come to class today or not? Things that we can measure as either yes or no, A or B. So let's remember that statistics is math that is concerned with uncertainty in relationships and mathematically modeling that uncertainty. So when we talk about correlation, we want to think about, given a certain amount of uncertainty, what can we say about the relationship between any independent variable and a dependent variable? And that's really where we're going to be going in the class for the rest of the semester. When we look at a relationship between two variables, we call that a bivariate relationship. Bi meaning two, variate referring to variable, so bivariate, two variables. So if I talk about a bivariate relationship, I'm talking about how x and y, or a and b, are related. If we are going to talk about many variables, more than two, we call that a multivariate analysis or relationship. More on that later. But you've seen actually in class so far a number of ways that we can look at bivariate relationships. If we think back before the midterm, you've seen how you can make simple comparisons between variables using means, modes, looking at dispersion, using standard deviation. You've seen how you can use a simple crosstab, a table, to visually examine a relationship, look at percentages. You've seen how you can use the chi-squared test to mathematically say with a certain level of statistical significance whether or not a relationship appears to be real or not, whether or not two things seem to be related, and then a number of other less common tests, but like Summers D and Lambda, that they are used, but not as commonly, but they also look at bivariate relationships. And you've also seen difference of means tests. All of these are techniques that we've looked at, some more mathematical than others, that give you some tools to analyze a bivariate relationship. This slide here should not intimidate you. Where I want to go with the rest of this lecture is to get you to start thinking about how we can talk about correlations or relationships in a more quantified way. So more into the habit of using numbers, a little less about qualitative assessments. You have seen some ways that we can start to do this in the last chapter. Lambda, Cramer's V, Summers D, all of those are statistics that tell us the direction and the magnitude of the relationship. But again, they are somewhat less common as statistical tests. The most common way to talk about correlation is what we call Pearson's product moment correlation coefficient. That's a long name. Sometimes it's just called Pearson's R. Sometimes it's just called the correlation coefficient or the correlation. But whatever term we might use, this is the most common way of assessing correlation mathematically in statistics. We represent it as the lowercase letter r, typically italicized. And Pearson's R is a measure of the strength of the linear relationship between two variables. That's a very important point, and why I have linear relationship in red. Um, the math of what Pearson's R is doing is that it is essentially trying to see in the overlap between two variables, how strongly do they form a neat line? Um, that's effectively the best way to think about what the math is doing in a more verbal kind of way. To the extent that two variables overlap, how strongly do they form a line that's not flat? A flat line indicating 0. So if the relationship between two variables is not linear, not forming a line, then a correlation coefficient is really not the best way to try to assess the magnitude of that. So think about, for example, interest in politics and how that aligns with partisanship. Generally, the people who are the most interested in politics are your strongest partisans, your strongest Democrats, your strongest Republicans, and the people who are the least interested are purist independents. So if we had to graph how partisanship and interest in politics matched up with one another, and just imagine that we have partisanship on the x-axis and interest on the y-axis, it's going to form a U. It's not going to form a straight line. So that relationship that looks like a U, that's not linear. Pearson's R would be a very bad way of assessing that, which is often why we might visually inspect our data before we run statistics on it. But I think that's an interesting example for really illustrating the point that what Pearson's R is doing is it's assessing a line and how much of a line is present in the data. Mathematically, Pearson's R ranges from -1 to +1. So if we have an R that is -1, that indicates a perfect negative linear relationship between variables. Negative meaning, you're familiar with this term, that more of one variable corresponds to less of another. If we were to graph that, that would be a line that slopes downward. So a perfect downward sloping line might be represented with a -1, a perfect negative linear relationship. An R of 0 indicates no linear relationship between variables. You might visualize that as flatness, the x-axis, a line like that. No line that we can form that slopes up or down, so no relationship. An R of +1 indicates a perfect positive linear relationship. Positive, again, you know this term, that means that more of one thing corresponds to more of another. So you might view this graphically as a line that slopes upward. But regardless of whatever R is mathematically, it's always going to be bound between +1 to -1. 0 is no correlation, no relationship, and the strength of that relationship, the strength of that correlation grows the closer we get to 1, either positive or negative. Mathematically, Pearson's R is most appropriate for ordinal, interval, and ratio level variables. It's not very fit mathematically for nominal level data, though we will sometimes see some people using it for that, which drives people like me crazy. If you have a nominal variable involved in your data and you want to talk about a relationship, you're better off using the chi-square test and exploring the relationship out from there. So this is a technique, Pearson's R, that is more appropriate for some type of data than others. Pearson's R does not care about how variables are scaled, whether they are 1 to 7 or 1 to 10 or 1 to 100 or what the verbal quantities of those are. We just need them to fit the profile of an ordinal, interval, or ratio level variable, and that scaling does not affect the calculation. One thing that's important, though, to realize about Pearson's R is that it says nothing about statistical significance in and of itself. So this is not something that's going to say what the likelihood is that a correlation is real or not. There's no 95% confidence interval. There's no 0.05 level of statistical significance. It's simply a measure of linear overlap and how strong that overlap is. Like a few other things that we've seen in this class, we will often use slightly different notations or formulas when we're talking about a population versus a sample for the correlation coefficient. So there are two versions of how we can talk about this and represent it or calculate it. It's worth pointing out that when we think about what statistics is really about samples. It's not about populations necessarily. Statistics is about inferring from samples to populations. When we cannot observe the entire population, we take the sample and then we make an educated mathematical guess about what things look like in a population. And that is really what statistics is about. When we do a sampling, that's where something like uncertainty becomes very important. Because when we infer from a sample to a population, we want to talk about how certain we can be about those estimates. It would not make sense to talk about certainty or uncertainty when we have all the data on a population, because you can observe the entire population and you know exactly what all of the data are. Correlation is one of those things that it actually does make sense to speak about it in terms of a sample or a population, because it's just overlap in data that you can observe. And it doesn't really matter from a conceptual level whether we're talking about data in a sample or a population. Also useful will be means, medians, modes, standard deviations, and even the regression techniques that I'll teach you about. They could be used on populations as well, though the uncertainty aspect of some of these things is far less relevant or even not relevant when we talk about populations. But at any rate, let's focus on the Pearson's correlation coefficient here. When we talk about a population correlation coefficient, we use the letter P to indicate that. Again, P is a very versatile letter. You often have to interpret it in context. I know that's a little frustrating. I wish I could go back and fix the history of how all of these things became notated over time. In practice, we don't talk about population correlation coefficients that often. So typically, especially in this class, when you see a P, you're going to interpret that as a p-value for statistical significance. But just know that P also sometimes means population correlation coefficient. Typically, we're dealing with samples, and we deal with samples in this class. When we talk about correlation in a sample, so a sample correlation coefficient, we are going to use the lowercase r to indicate that. So if you go back up and look at the title of this slide, calculating r sub xy, we can actually understand what that means now. R is a sample correlation coefficient. X and Y are two variables that we want to examine the correlation of. So R sub xy means the correlation between X and Y in a sample. Easier than it looks. So let's look at the two formulas now for calculating this in a population and a sample. So here let's look at how we can calculate the correlation in a population. P sub xy means correlation in a population, and that is equal to the covariance of x and y over the product of the standard deviation of x and the standard deviation of y. There are several different ways that we can represent this formula. What you see here are the two most common ways. It often all comes down to what shortcuts you want to take with showing the math, and people have different preferences over that. Let's talk about the numerator here. So the numerator in that formula on the left is the covariance, and it is a generalization of the variance of two variables, or a general way of expressing how two things vary. It is a measure of the degree to which x and y tend to be large together or small together, or one is large while the other is small. That's the idea of a pattern in data or covarying or occurring together in some way. It's not on any standardized scale like positive to -1. That's a standardized scale. It is bound to infinity on the positive side, and it's bound to negative infinity on the negative side. So it doesn't have any clear limits to it. But what's important for us to think about covariance is whether that value is positive, negative, or zero. And that's really what's going to matter to us in this in this formula here. So to calculate covariance, there actually is a way we can do that, and you see that on the right. So here we see it's the sum of x minus mu sub x times y minus mu sub y. So let's unpack this. So if we have two variables x and y that interest us, for every unit or observation in our data, or for every person in our sample, we're going to subtract the population mean of x and y from their observed scores of x and y, and then multiply those together. So let's say that we have two feeling thermometers, for example, and I'm respondent number 1 in the survey. I've rated two things, however I'm going to rate them. It's between 0 and 100, and the ratings of those two things are that uppercase X and the uppercase Y. That's how Patrick Miller or anyone else in the class individually rated those two things. But then there's also an average for the entire population, and that's the mu sub X. So X minus mu sub X, if we're talking about a survey of a population, we could think of that as how Patrick Miller rated whatever the first thermometer is assessing, chocolate maybe, or ice cream, minus the average of how everyone in the population, or whatever else that is. We also have some other thing, the Y, that we're assessing here. So that's how Patrick Miller rated whatever Y is, minus the average of how everyone in the population rated Y. And so we can do that for everyone in our survey. If we have 1,000 people in our survey, we're going to do that 1,000 times and multiply those two numbers together. And then we're going to add all of those up. And that will give us some numerator on top. And that's going to be our covariance, which is really only useful here for telling us positive, negative, or zero. That covariance, it's going to tell us about the direction of the relationship, but tells us nothing about the magnitude. To turn that into something that's going to tell us about magnitude, we need to standardize this value. And we're going to do that by dividing by the product of the standard deviation of x and the standard deviation of y in the population. And you're familiar with standard deviation, so again, just come back and think of this. Where can you get all the pieces of information here? If we're dealing with a population and we have two variables, x and y, we can certainly calculate the average of x in the population, that's mu sub x. We can calculate the average of y in the population, that's mu sub y. We know enough to be able to calculate the standard deviation of x and the standard deviation of y in the population, so those should all be understandable to you. And again, that capital X, the capital Y, that's how every person in the population that we're surveying or looking at rated X and Y. So this is a lot easier than it actually looks, and you just apply your mathematical operators of multiplying and then adding and then dividing, and that gives you P sub XY. Now let's modify that last formula. Let's walk you through another little example here. Let's say that we have a simple survey of 4 people. I'm not sure why we would ever do a survey of 4 people, but it simplifies the math for us. And we have an X and Y, whatever they happen to be. And in parentheses here, we see how every individual answered on X and Y. So individual 1 has values of 1, 1. Individual 2 has values of 2, 3. individual 3 has 4, 5, and individual 4 has 5, 7. So we have 4 sets of responses here. And let's say we want to calculate R, or the correlation of these two things. So we can put all of our little pieces together to do this. The average of the x values is x bar, and that is 3, pretty simple. The average of the y values, that's y bar, or hat, as we sometimes would say, that is 4. The standard deviation of x, using the formula that we've learned so far, is 1.83. Standard deviation of y is 2.58. So all of that is stuff we learned before the midterm. We can apply what we learned on the previous slide for calculating zx and zy. Zx here would be for every individual, the observed value of x minus the sample mean of x over the standard deviation of x. So for individual 1, that's negative 1.09 plus additional values beyond the decimal point. For individual 2, it's negative 0.54, and so on and so forth. We can calculate the z sub y for each individual, and so this is their observed value of y, the y that they gave us, the y that they answered, minus the sample mean of y over the standard deviation of y. And then, so for individual 1, that's negative 1.16, and so on and so forth. We can then multiply for every individual z sub x and z sub y together. So for individual 1, that's 1.27. We can add all of those up. We can add up all those for zx, zy, or z sub x, z sub y. If we add up all those values, that's 2.96. And that gives us the numerator for calculating the correlation coefficient in the sample. And the denominator is n minus 1. So the denominator here is the number of points in our data set, in our paired data. We have 4 points here because we have 4 people in the survey. So n minus 1 is 4 minus 1, which is 3. So we will divide 2.96 by 3, and that gives us a correlation. It gives us an R of 0.989949. This is almost 1. So if we remember, R is bound between positive 1 and negative 1. So if we have a correlation here of 0.98, 0.99, this is almost a perfect positive correlation. Here we can just look at transitioning over into how we can look at this visually. We can look at some typical perfect relationships, perhaps. On the far left in this figure, we have a positive correlation or a positive covariance, which means that larger values of x tend to go with larger values of y, or smaller values of x tend to go with smaller values of y. So two things move together in the same direction. So we could illustrate this with that positive correlation figure where we have the line that slopes up. In the middle, we have a negative correlation, a very nice looking negative correlation. This means that larger values of x tend to go with smaller values of y, or smaller values of x go with larger values of y. So as one variable moves in one direction, the other variable moves in the opposite direction. And here we might look at that as a line that slopes to the bottom right, slopes downward visually. On the far right, we have a flat line, effectively. There's no correlation here. In fact, it's a little misleading to even represent it as a line. It's just flatness. It is the absence of a relationship. It has no positive or negative slope to it. This would be perhaps a correlation of 0, or very close to it. Here's where I want to complicate that last slide just a little bit to remind you that correlation, and it's sometimes called covariance, as your book talks about, that it is only a measure of how linear a relationship is, the measure of how good or clean of a line that we would observe in the overlap between two things. It does not necessarily care about what the slope of that line is. And so, regardless of the relationship between two variables, the more nonlinear it is, so the more messy it is or the more curvy it is, the closer r will be to 0. So let's just look here and unpack what we see over here on the right visually. And look right there in the middle of the figure. We have what looks like the flat line going right across the middle. And this represents what I showed you on the previous slide. This is really the absence of a relationship. This is a 0 correlation. I'm not sure why it's not actually labeled 0. I stole this figure from someone else. But it's flatness. There's no slope to this. That would be a correlation of 0. Just like everything on the bottom row is also a correlation of 0. There is no line in any of those representations of data clusterings on the bottom. So all of those are 0, even though there are clearly relationships in those data. Pearson's R would tell us the correlation is 0. If we look at the top and we look at the figure in the middle on the top row, that is just a circular cluster without any kind of hint of a line to it, that's also a correlation of 0. So a correlation of 0 can look like a lot of things. Let's look at the things that are denoted as correlations of 1. So in the middle row, that's the 3 lines on the left. It's also the line on the top and the far left. All 4 of these lines, they have positive slopes on them. Some of the slopes are steeper than others. So, for example, on this middle row, the further we get to the left, the steeper that slope is. But all of these would have correlations of 1 because that line is very neat, very clean. All of the data form a perfect line together. There's no messiness in that. And so all of them would have correlations of 1, even though the slopes are different. So keep that in mind. You see the same thing here with negative correlations on the other side of the figure, where we have 4 lines that have negative slopes. Some of them have different slopes, different steepnesses to them. But the lines are very neat, they're very clean. There is strong clustering along the line. So these are all perfect negative correlations, even though that line is steeper for some relationships than others, which leaves us with the in-betweens on the top. If we look, for example, at the visual for a correlation of 0.8, we see a general pattern here that slopes upward. It's not a very neat line. It's messier than the correlation of 1, but it certainly indicates a positive relationship. But there's a fair amount of clustering along what an imaginary line there would look like. If we look at the correlation of 0.4, that gets even messier. We can see visually here, based on the density of the data, that there is a positive relationship, but it's not a neat line. And so we're going to have a weaker correlation here. And we see the inverse on the other side with the negative correlation coefficients. So just be very aware of what the correlation coefficient is actually measuring. It's measuring the strength of a line, the neatness of a line, how much the relationship between two variables perfectly represents a line. The messier that line gets, the weaker that correlation gets, up to the point where we might have a correlation of 0, as indicated by any of these other figures. So always keep in mind that we need to interpret a correlation in the context of linearness or linearity. And always remember what it is that we're exactly talking about here. So let's use some stata here. I want you to know conceptually what a correlation is calculating. It's very important to know what a correlation is and is not in terms of a line. I want you to know conceptually what the formula is for calculating a sample, a correlation in a sample. I'm not going to make you do that on the exam, but you certainly might see a question about what conceptually is happening there. That would be torture to make you take a data set and really do that. It's one of the harder things, more involved, we can do by hand. Luckily for us, we can save ourselves a lot of that pain. Using Stata. This is a very quick and easy thing to calculate in Stata, even with a data set of thousands of respondents. But again, I do want you to know what it's actually doing so that you can talk about the correlation coefficient intelligently. There are two useful functions in Stata for understanding correlations. One is creating a scatter plot to assess a relationship visually, and then actually using the proper command to calculate mathematically what Pearson's R is. So let's walk through some examples from one of my recent surveys that I've conducted and look at how we can do this. So this is from a survey that I conducted, I believe, 2 years ago, just on a variety of different things. This might have been one of the surveys we did about transgender rights attitudes, but we had stuff not related to that topic in there. Here we have a scatter plot, and you should be familiar with that, of respondent age on the x-axis and the feeling thermometer towards Muslims on the y-axis. This is a great example for illustrating how in the real world, data are not always neat and clean. It's very rare that we see perfect correlations of 1 or -1 that just line up on this beautiful line. It's always a little messier or a lot messier, and it's always a bit harder to interpret. So on the left in this visual, this was a survey, I believe, with 1,000, about 1,000 respondents. I think 1,020 respondents in it. And so here's the scatter plot for the entire sample. You can look at this and see, you can tell a couple things about the data. First, just looking at the distribution of age, there are not a whole lot of people above 80 in the survey. There are some people there. Certainly it's more clustered towards middle-aged and younger people, or senior citizens in the 65 to maybe 80 range. But if we look at how that overlaps with the thermometer score, you can detect a bit of an absence of data in the upper right. So the density of the data is not as thick in the upper right, which indicates we have fewer people who are older but rate Muslims very warmly. It's obviously not a super strong relationship, but it does appear to be there. If you look at where the densest lines are, you can see that there's a denser cluster of people who rate Muslims at the midpoint, the 50, that's that more solid almost line going across the middle. There's a nice chunk of people who rate 100. There's a nice chunk of people who rate 0, and people are otherwise scattered in between. On the right, this is just, I use the sample command in Stata. So sample 10 means randomly sample 10% of my data, and then use the scatter plot command again, which is scatter whatever your two variables are, your y-axis variable and your x-axis variable. So this is just 10% of my data. And you can see that pattern a bit clearer here, I think, with the absence in the upper right. So all things equal, before we even get to calculating the correlation coefficient here, we can probably guess that this is going to be a negative correlation of some kind, that the older you get, so the more age you have, the colder you're going to rate Muslims, probably on average at least. So the less warmly, the smaller thermometer scores one would have. Though obviously, even though we're guessing that this is a negative correlation, that doesn't mean that's still a generality, right? There are still young people who rate Muslims very poorly. You have some, young adults who rate Muslims 0. We obviously have some older people who do rate Muslims pretty warmly. So we're talking about a general negative relationship here. There are obviously going to be people who deviate from that generality, and that's okay. So remember that what the correlation coefficient is it is fitting a line to the data. It is asking how good of a line is created. And so even though this is a rather messy set of data here, it's not a perfect line in the raw scatter plot, we can tell Stata to actually fit the best line to this 10% subsample that I did on the previous slide. So the data are arrayed as they are, and then we can tell Stata, draw the best possible line to represent the average relationship in these data. And we can use that with the 2a command. So 2a, and then in parentheses, scatter Therm Muslim's age to the y-axis and then the x-axis, and then close the parentheses. In a new parentheses, lfit, so line fit, lfit, Therm Muslim's age again. And again, what this is telling Stata to do is to draw the best line through this scatter plot to represent the average relationship. We know that we're not going to hit every data point here. There are certainly dots that are not on the line. All of the dots are going to influence the average relationship here, but we're going to draw the line that best represents the average relationship. And if we tell Stata to do that, the fitted line, Stata calls this the fitted values, we see that this is a negative sloping line. It's not a very strong one, since again the values themselves are rather of a jumbled mess, but we do see our suspicion that this is a negative relationship seems to be backed up by fitting the best line to the scatter plot. We can then use the simple CORR command, or type out correlate, the correlate command, to actually now calculate Pearson's R for the Muslim Filling Thermometer and age. And so if we do that, core Therm Muslim's age, we see that we have a correlation coefficient of negative 0.13. So that mathematically reinforces for us that this is a negative relationship. However, remember that Pearson's R is bound between +1 and -1. And so, negative 0.13 is a lot closer to 0 than it is to 1. So this is a rather weak negative relationship, but it is a negative relationship nonetheless. If you look at the ones, that's just telling you that each of the two variables in the correlation correlates perfectly with itself, which is obvious, right? If you turned the x-axis and the y-axis both into age, you plotted the same piece of data on each axis, you would obviously graph a perfect line. So it's that off diagonal there. That's what we call the negative 0.13, the off diagonal. That's the key number we want to look at here. We can actually play with the data a little bit more. Here, let's show you some stronger correlations. This is the same data set. And so here I have filling thermometers for Vladimir Putin, Donald Trump, Hillary Clinton, and Bernie Sanders, and how those match up with our 7-point partisanship scale again. So on the Putin filling thermometer, we have a correlation of 0.39. So the way we would interpret that is that's a pretty moderate relationship. It's certainly stronger than the relationship of the filling thermometers on race to partisanship. So all things equal, the more Republican someone is, the more warmly we expect them to rate Vladimir Putin. And you can see that we have the fitted line here that is positive, it's sloping upwards. You can see on the far left that strong Democrats would rate Putin somewhere in the ballpark of a 20 on average. Strong Republicans would rate him almost a 60 on average, so on the warm side of neutral. So that's a stronger correlation than we saw with race. If we look at the Trump and the Clinton feeling thermometers, those are even stronger. So 0.57 for the Trump thermometer. Remember that higher values of partisanship are stronger Republicans, so the more Republican one becomes, the more warmly one should rate Trump. And then you can see the fitted line and where those values correspond on the y-axis. The inverse of that is the Clinton thermometer. It's a negative 0.56, so that's a healthy relationship there. The more Republican one is, the less warmly, all things equal, they should rate Clinton. And we can see that in the downward sloping line for the Clinton thermometer. The strongest correlation in the data is actually for the Sanders feeling thermometer, which tells us that there is the greatest overlap of the 7 thermometers we've looked at here. There's the greatest overlap between partisanship and the Sanders thermometer. You could also think of that as Bernie Sanders as the most polarizing of all 4 of these political figures or the 3 racial groups that we looked at. He's the person who most drives Democrats and Republicans apart in the data. This is a correlation of negative 0.67. So the more Republican one is, the less likely one is to like Bernie Sanders. And we can see that here in the scatter plot. It certainly pans out visually. And we can see that with the fitted line as well, with your strongest Republicans rating him on average almost 0, and your strongest Democrats rating him about a 70, somewhere in that ballpark. I want to do a little bit of an exercise here to illustrate a point that's going to become very important when we get into regression, which is, again, just fancy correlation. In practice, it is actually really hard to find 2 variables that are almost perfectly correlated. It's certainly hard to find that in political science data if we're dealing with political variables a lot of the times. So because I don't have one that's easily available, I'm going to create one for you in Stata. And here what I'm going to do is I'm going to create a 4-category age variable that is based on a recoding of the full age variable in my survey that runs from 18 to 99. So my youngest respondent was 18, my oldest was 99. So rather than having 18 to 99, I want to create these 4 age cohorts, and then I want to graph the 2 age variables against one another. So on the y-axis in my figure here, you see the 18 to 99. On the x-axis, on the y-axis, you see the age cohorts. So it's not necessarily important that you understand all the recoding, but I'm going through the proper steps here to create a new variable I'm calling age 2. You could call it age cohort, whatever. And then I'm using the replace commands to put people in their proper age groupings. And so I have that age cohort measure now. And if I graph them against one another and I use my lfit command, you can see how these pan out. I mean, this is a much neater relationship than we saw with the feeling thermometers. It's a much neater line, though obviously not a perfect line. But if we calculate the Pearson's R, we see that this is an incredibly strong correlation. It's 0.96. It's not going to be perfectly 0.1 because of how I did the age cohorts. But this is a super strong positive correlation, obviously because it's 2 ways of representing the same variable, age and age. And this is actually a really useful example. When we get into regression, we'll come back into the idea of correlation, because in a regression, it is not good to have variables that are too highly correlated. The math of regression begins to fall apart when that happens. And the reason why it's bad is because if you have two variables that are too highly correlated, that indicates that they might just be two ways of measuring the same exact thing, as you see here with two ways of measuring age. Just to preview that a little bit, in the regression world, if we have two variables that correlate at 0.8 or above, we don't want to have both of them in our formula that we use to run our regression model. People disagree about what that cutoff is. Some people say higher, some people say lower. I think a good rule of thumb for our purposes in this class is 0.8. So if you ever see a correlation, just run with that of 0.8 or above. You should be a little suspicious that the two variables that you're seeing the correlation for, they might just be two different representations of the same underlying concept. You've measured the same concept in two different ways. But I think this is a useful point to point that out. You want to be suspicious of those super high correlations. I want to make one final point about correlation that really pits the math against the reality of this. And that is, what happens when we ask what is a strong correlation? The answer is a little subjective. So obviously, if we just look at the pure math of a correlation is, we know that a 0 is no correlation. We know that a positive 1 or a negative 1 is a perfect correlation, a suspiciously perfect correlation. You probably have actually measured the same concept in two different ways. But if we just go based on that 0 to 1, positive and negative 1 scale, and think of that as our spectrum of possible values, then we might say something like what this visual says, that a strong correlation is a 0.7, 0.8, 0.9, whether that's positive or negative. A moderate correlation is a 0.6, 0.5, 0.4. A weak correlation is a 0.3, 0.2, 0.1. And if you're going to use just the entire scale, I think that's a fine way of looking at it. However, I want to bring in here what happens with measurement error and response error. So you know that when we are dealing with human beings in surveys, there is error that comes into that response process. And the consequence of that is that error makes our correlations look weaker. So for example, if you go back earlier in this slide, you've heard me say enough by now in class that partisanship is often the biggest divide in our politics. It's the most polarizing divide in our politics, especially when we start thinking about evaluations of presidential candidates. All things equal, evaluations of Trump and Clinton or a Bernie Sanders should be the most polarizing thing that we could ask in a survey. But even though that is actually the case, that is actually true, evaluations of those candidates is often where we see the biggest divide between Democrats and Republicans. Even though that's where we get the biggest polarization, we're still only seeing correlations of 0.5, 0.6, 0.7 in the data that I showed you earlier when we correlated the Phillian thermometers for Trump, Clinton, and Sanders with the 7-point partisanship scale. So that illustrates the point that when we deal with survey data and we deal with the error that comes into that, we should typically expect correlations to be lower because of error in the data. So if you're asking, well, what is a strong correlation? If you look just at the spectrum of Pearson's R, then a strong correlation, in this case, 0.7 or above. But realistically, when we analyze survey data, the strongest relationships, the most polarizing relationships that are going to yield the biggest Pearson's R might only be about a 0.5, a 0.6, or a 0.7. So in practicality, in survey data, because of error, A strong 0.5 might be a strong relationship. 0.6 might be a strong relationship. There's so much error that goes into the response process that it's often unlikely that you're going to see those 0.7s, 0.8, 0.9s with attitudes. And so if you're dealing with survey data, you might often rescale how you think of this. So with survey data, if a 0.5 is strong, maybe a 0.3 is a moderate relationship. A 0.4 is a moderately strong, a 0.2 is a moderately weak, and a 0.1 is still a weak relationship. So I think that that's going to be useful for you when you use Pearson's R in your papers, because you might have some hypotheses that you're testing where in the crosstabs it looks like you have very strong polarizing relationships, but you only see a Pearson's R of like a 0.5 or a 0.6. And that's because of that error, right? So adjust your expectations with survey data for what a strong correlation is. Don't tell me with a survey that there's only a moderate correlation between the feeling thermometer for Clinton and Trump and partisanship. Don't tell me that's moderate because the correlation is only 0.5 or 0.6. In the context of a survey, that's actually super strong. These next few slides. On this slide, we're again looking at state-level data, and we see the percent female household with no husband present, so single female household, and percent in poverty. And we're plotting these two things against one another. So let's think about this in the same way that we thought about the previous slide. It's pretty obvious here that we have a positive relationship in the sense that as percent female household increases, percent in poverty increases. So if we look at our options to the right, we can automatically rule out options B and C, which indicate negative relationships. So now we're down to A, D, and E. And here we really do have to judge, well, what does the strength of this relationship look like? Let's look at option D for a second, a correlation of positive 0.9. Remember that correlation is bound between positive 1 and negative 1. So a correlation of positive 0.9 would almost look like a perfect line. It wouldn't be a perfect line, that would be positive 1, but this would almost be a perfect line. So we can look over here and ask ourselves, do we almost see a perfect line in this graph? And we really don't. So I think we can rule out option D, that the correlation is not that strong. If we look at option A, a correlation of 0.1, remember that a correlation of 0 is no relationship whatsoever. So a correlation of 0.1 would indicate a very weak positive relationship. If this were a correlation of 0.1, we would have a hard time looking at this and really deciphering the relationship. Probably a harder time than we're actually having. So I think we can rule out option A because we can clearly see that this is a positive relationship. And that leaves us with option E, a correlation of positive 0.5. So among the 5 options that we have here, that really does appear to be the best option for labeling the strength of this relationship. On this slide, we have a different type of question where we're being asked which of the following scatter plots has the strongest correlation. So in other words, a correlation coefficient that is closest to the bounds of positive 1 or negative 1. And we have 4 options here. Well, based on what we've learned, we can rule out option A because remember, with a correlation, we are thinking about the extent to which the data form a line. A line is straight, a line is not curved. So we can rule out option A because correlations are not really designed per se to look at a curvilinear relationship like this, as was talked about in the lecture. So we can rule out option A as being one that is clearly wrong here, even though, it's a relatively clean curve. It's just not appropriate for the correlation coefficient, which leaves us with B, C, and D. So remember, the stronger the correlation is, the neater or the tighter the line will be. So effectively what you're being asked with B, C, and D is which one of these scatter plots has the cleanest line? And the option is clearly B. So if we look at B, this would not be a perfect correlation because we do not see a perfectly neat line here, but it is closer to being that than C or D. So B would be your strongest correlation here. This question is maybe a little more challenging. So here we're going back to that graph of percent high school graduation in a state and percent in poverty. And we have 4 lines that are plotted over the data, A, B, C, and D. And you're being asked which of the following appears to be the line that best fits the linear relationship between these two variables. So if we look at these 4 options, let's think, what can we rule out automatically as being an unlikely option? Well, if you remember our discussion of this slide earlier, we are clearly able, from this scatter plot, to discern a negative relationship here. So I think we can automatically rule out option C, which is that dotted violet line. That's a flat line, and a flat line like that would really indicate a correlation of 0. And so that's probably not a very likely option. So why don't we rule out option C, which leaves us with the 3 options that actually do indicate a negative relationship. I think we can also rule out option B, which is the dotted green line here. Even though it indicates a negative relationship, it's really not going anywhere near the heart of the data. With a correlation, we're trying to make the best line through a scatter plot, and it should really take us as close as possible to as many of the data points as we can get. And keep that in mind, because that will be important in the next component of this lecture when we talk about OLS regression. So I think we can rule out option B, because option B is really at the periphery of the scatter plot. It's really not a line of best fit in the sense that it's not getting us as close as possible to the data points. It's just too far off in the extremes. That leaves us with option A, which is the brown line, and option D, which is the blue line. So let's think, what would be the best line through the data here? And I would argue it's option A, because option A is seeming to take us really through the heart of the data. And if we especially look at it on the far left and the far right, it's not really flirting with the extremes of the graph in any particular way. Unlike option D, where, even though the middle of this line is relatively in the heart of the data, look at where it is on the extremes, on the far low and the far high end of correlation. It's really off playing with the outliers at the extremes. So I think here you would be best served to choose option A as the line that best fits this linear relationship, because it's really the line that most goes through the heart or the center of the data at all points on the graph and doesn't take us too far into any of the extremes. So again, just to sum this up, if you can understand what bivariate correlation is, then you can understand the logic of everything we're going to do from this point out, with OLS regression in particular. Ordinary least squares regression, OLS regression, it is just fancy correlation. It's way more useful than Pearson's R, but Pearson's R and the logic of that is really where you have to start. So, in this lecture, I think if you understand what correlation is, you understand conceptually what the formula for correlation is. I mean, where does this number come from? It's not black magic. It doesn't come out of thin air. And then you understand how we can use Stata to calculate that and explore the data a little bit. Then you're good. You have a solid foundation for understanding OLS, which is where we'll go next.